Hello everyone, welcome to video number 4 of composite sections, analysis of stresses in composite sections. In the previous video we discussed about and solved the problem on the analysis of stress when the modulo of the precast units and cast in situ slab is same, but in this case the modulo of that is elasticity of the precast units and the slab is different. That we will discuss today, and we will solve the one more problem on this analysis of stresses in composite section. The problem goes like this: a precast pretensioned with a rectangular section of size 120 millimeter by 240 millimeter is used a part of composite beam to span of 6.25 meters. This unit is pre-stressed by tendons with their centroid coinciding with the bottom kern point. The initial force in the tendon is 240 kilonewton. The loss of pre-stress may be assumed to be 15%. The unit is incorporated as the web of a composite beam by casting a slab of flange width 480 millimeter and thickness of 40 millimeters. On the top of the precast unit, the composite beam supports a live load of 4 kilonewton per meter. Calculate the resultant stresses developed in the precast and cast in situ concrete, assuming the pre-tensioned unit as unpropped while casting in situ slab. The ratio of moduli of elasticity between precast unit and cast in situ slab is 1.25. The given given problem is precast beam first. The width of the section precast unit only 120 millimeter, depth is 240 millimeters. The span is 6.25 meters and the pre-stressing force in tendon is 240 kilonewton and 15% loss is given, therefore eta factor will be 0.85. Cast in situ slab section properties are 480 millimeter width, 40 millimeter depth, and centroid of the tendon coincides with the bottom kern of the point. With the help of this we have to calculate the eccentricity of the cable. The eccentricity will be, if you make 3 parts, the upper kern will be 80 millimeter from the top, and similarly bottom kern will be 80 millimeters, and the eccentricity will be from the center, as it is rectangular section, centroid will be at the center, and position of the centroid of the tendon is equal to 120 minus 80, that is 40 millimeters. And one more is given, the Young's modulus of precast unit and the slab is different, therefore the ratio is given 1.25, that is Young's modulus of precast unit divided by the Young's modulus of the slab is 1.25, that is 25% more than the slab. And solution here is stress at top and bottom only due to pre-stress, that is in precast unit or the precast beam. As we know the formula P by A minus plus P by Z. If you take top minus sign, bottom is the plus sign. For that we require the area of this section 28.8 into 10 raised to 3 millimeter square, and the ZT or ZB is same, it is a symmetrical section, BD square by 6. The value is equal to 115.2 into 10 raised to 4 millimeter cube. Stress at top P by A minus PE by Z comes to be 0 because the centroid of the tendon coincides with the bottom kern, and the bottom is similarly P by A plus PE by Z, that is will be twice of the P by A or 16.66 Newton per millimeter square. And we have to consider the loss given. After all losses, what will be the stress at the bottom will be equal to eta factor multiplied by the stress calculated, that is equal to 14.16 at the bottom, top will be 0 of the precast unit or the precast beam. It is a given section, cast in situ slab 480 by 40 and the precast unit is 240 by 120 millimeter. And first we have to calculate the self weight of the precast beam, that is ZP, suffix P is given as the precast unit 0.12 into 0.24, 24, 0.69 kilonewton per meter. Moment due to self weight of precast beam is 0.69 into 6.25 square by divided by 8, that is W square by 8, that value will be 3.375 kilonewton meter. And the corresponding stress due to precast beam at the top and bottom is same because it is the rectangular section, symmetrical, 3.375 into 10 raised to 6 divided by the section modulus of the precast unit is 115.2 into 10 raised to 4, the values will be plus or minus 2.93 Newton per millimeter square, that is at top and bottom. Similarly, we have to calculate the cast in situ slab. Self weight of slab GS is 0.04 into 0.48 into 24, that value will be 0.46 kilonewton per meter. Corresponding moment due to slab is MGS 0.46 into 6.25 square divided by 8, that value will be 2.25 kilonewton meter. Similarly, we have to calculate the stress at top and bottom. It is given is unpropped condition. For that we have to take the stress at top and bottom section modulus of the precast unit only for the unpropped conditions. Therefore, 2.25 into 10 raised to 6 is the moment due to slab, and the value will be plus or minus 1.95 Newton per millimeter square. That is section modulus of precast unit you have to use it. And section properties of the composite section, total we have to take as cast in situ slab as well as the precast unit. Let YT and YB be the distances of centroidal axis from top and bottom respectively. That composite section, YB is equal to, as usual you have to calculate same area multiplied by the distance from the bottom up to the composite centroidal axis, which is YB, we don't know, plus here I have taken as 1.25. This is the Young's modulus of precast unit is more than cast in situ slab, that is 25%. It is given 1.25. If it is 1, you can use it as a 1, then it will be, as usual you have to calculate the YB and YT. Wherever precast units comes into the picture in the calculation of YB, YT or the moment of inertia, or if it is stress, we have to use the 1.25. Similarly, that value comes to be YB is equal to 162.82 millimeter, YT is equal to 111.18 millimeter. The YT of composite section is 111.18 and YB is 168.82, and then we have to calculate the moment of inertia of the composite section, that is IC is equal to BD cube by 12 and area into square of the distance. Here we have to consider the 1.25 is the ratio of the modulo of the two cast in situ slab as well as the precast units. Therefore, 1.2 into bracket we have to calculate the BD cube by 12, area into square of the distance. Therefore, the moment of inertia of the composite section is 20.78 into 10 raised to 6 millimeter raised to 4. Then the live load is given as Q is equal to 4 kilonewton per meter, and the moment due to the live load is 4 into 6.25 is the span square divided by 8, 19.53 kilonewton meter. And stress due to live load at the top of the slab is equal to, that is we know that M by Z, that is 19.53 into 10 raised to 6. This is the moment of inertia divided by the YT, that is equal to 5.16 Newton per millimeter square. Similarly, at the bottom of the slab is same 19.534, 80.78, 71.18, the distance from the top up to the bottom of the slab, that is equal to 3.30 Newton per millimeter square. Similarly, we have to calculate the stress in precast beam due to the live load. At the top 19.53 into 10 raised to 6, it is the moment divided by the moment of inertia and into the distance 71.18, it is the top of the precast units from the top of the composite section. It is multiplied with the 1.25 once again, as it is the ratio of the moduli of the two different materials, that is equal to 4.12 Newton per millimeter square. Similarly, at the bottom same equation we have to use, moment of the live load divided by the section modulus. Section modulus 420.78 10 raised to 6 divided by 168.82, and it is multiplied by once again 1.25 as the given ratio. The value is 9.79 Newton per millimeter square. Next we have to find out the resultant stress at unpropped condition, which is asked. Here it is already we have calculated all these values, that is stress due to pre-stress only 16.66 and effective pre-stress after all losses is given 14.16 at the bottom, top is 0. Here it is stress due to precast unit and top plus 2.93 minus 2.93. And one more is stress due to slab. Here in case of unpropped conditions we have to consider the stress due to precast units only, that is a precast beam, that is 1.95 plus and minus 1.95 at the bottom of the precast units. Then we have to calculate the live load stresses. At the top 5.16, at the bottom of the slab is 3.30, and similarly we have to calculate the top of the precast units and the bottom of the precast units. Here top is 5.16 and bottom is 3.3 as usual, and top of the precast beam is, we have to add all algebraically in the precast unit, that is 2.93, 1.95, 4.1 to the total value is 9 at the top of the precast unit. Similarly, bottom of the precast beam is, we have to add algebraically all the values, 14.16 minus 2.93 minus 1.95 minus 9.79, that is minus 0.51, that is the value at the bottom. These are the stresses in the composite section, that is slab as well as the precast units due to unpropped conditions. Thank you very much. If you got any doubts, please contact me. Thank you.